Okay, good morning. So in the previous class, we have been discussing about the psychometric charts. Particularly, we discussed about the construction of the chart. We found that typically psychometric chart in different literatures is provided only at the ambient pressure conditions. If one has to study the properties of moist air at other pressures, then accordingly the chart construction has to be done using the property relations. Okay, on the psychometric chart along the y-axis we have specific humidity, which typically is specified in terms of kilogram of water per unit kilogram of air, where water refers to moisture content in the air and air refers to dry air. So typically whenever water and dry air are mixed, then we get moist air, but generally the content of moist air will be variable because the amount of water vapor in given amount of the dry air can be different at different thermodynamic states. That's why generally the standard condition or the standard approach is to specify the property in terms of the dry air content. So that's why we are using kGA. Now what we need to do, typically the water content is very small. That's why this number of specific humidity is usually very small. That's why we have multiplied this with 10 to power 3 in order to give some legible scale where one can actually properly look into the values. Okay, now along the x-axis we have temperature, and this temperature usually which we measure from thermometer, when its bulb is dry, then it is called as dry bulb temperature. Okay, if we see on this these are some curved lines. So this top curved line I have written phi equal to 100%. Here phi denotes relative humidity. So this line is having relative humidity 100%. It means this is corresponding to the saturated state of the moist air. Okay, and below this other curved lines represents the different values of relative humidity. Then on this line I have these black colored inclined lines. So black colored inclined lines are nothing but represents the constant wet bulb temperature lines. Then blue colored inclined lines represent the constant enthalpy lines. And usually on all the psychometric chart, if we extend these enthalpy lines, one inclined scale is provided, and this inclined scale typically gives value of enthalpy in terms of kilojoule per kg of dry air. Okay, and in addition to that we have some red colored lines. So these red colored lines typically represents nothing but the specific volume. Okay, and these red colored lines are constructed from the perfect gas laws, because usually the pressure at which we have this moisture present and the dry air, these follows ideal gas assumptions. Is this one clear? And other than that we have sensible heat factor. Of course, about sensible heat factor and alignment circle I will be now again discussing in detail. Okay, particularly in this lecture after few topics. Okay, and another interesting fact, we found that relative humidity, specific humidity, and other parameters such as dew point temperature etc are actually difficult to determine. Okay, so that's why what is usually and typically for specifying the thermodynamic state of moist air, we require three different properties. So one property is pressure, other property is dry bulb temperature, and third property becomes our wet bulb temperature, which usually we can measure by just putting a wet wick around the bulb of the thermometer. Is this point clear? Then other than that, of course, about dew point, wet bulb and dry bulb temperature, I already discussed in the probably in the previous lecture, where I specified that at saturated condition all these three temperatures are same, whereas for unsaturated air, dry bulb will be highest, then will be wet bulb temperature, and after that we will be having dew point temperature. Okay. Now, whenever we studied air conditioning or we defined air conditioning, then I told you that what we need to do, we need to process the air. Okay, so in terms of processing the air, what do we mean? For example, during this now winter season is approaching. So in winters, what we want in the room, heat. So what we need to do, whatever the air is there, that room air we need to heat. Okay. Second thing, in summers we do cooling, but in winters, you know that whenever we keep the heater on for longer duration, my air becomes dry. Did you observe this point? It becomes very dry situation. Okay. So basically, upon increasing the temperature of the air, its moisture holding capacity increases. Okay. So in order to go to the comfortable situation, what we need to do? We need to add some moisture. So if I need to add some moisture, it means I need to do humidification process. Okay. In summers, if you see, air is very hot, and because of the hot, particularly in the region close to the rivers, close to sea, we see there is a significant amount of moisture is holded by that hot air. Okay, so it means we feel excessive moisture in the air. So there our purpose is to dehumidify the air. So basically, in general, we need to either do heating, humidification, or cooling, dehumidification, or it may be the case of cooling and humidification depending upon the moisture content and other things. Okay. So in order to design the components for doing all these operations, first we should know that how thermodynamic equations will be applicable for these different type of processes. So first let us simply talk about a process which represents the heating of moist air. Usually, can you give me some example with the help of which we typically do heating of moist air in the room? Have you seen a blower, electric blower? Okay, so in electric blower there is one electric coil to which electric energy is supplied, which typically increases the temperature of that coil, and you see that coil is bit red colored sometimes whenever we are keeping it at the high temperature conditions. And in the blower continuously one fan is revolving, and either from the top portion or from the bottom portion of the blower, one hole with the small net like structure is provided. Okay, so through this hole what happens, air from the room gets into the blower, and then that air is passed over that red hot coil, and at the exit of the blower typically what we observe is actually hot air. Is this point clear? Now what we need to do, so here also similar thing we are having. Say from this point air is coming at m dot a flow rate, and W1 is its humidity, and here I have some heating coil. So this is nothing but a heating coil. When air will be passed over the heating coil, this heating coil will add certain amount of heat. Okay, and at the end again I will be getting the same mass flow rate of dry air because I am not doing any operation, and say my relative humidity is specific humidity is W2. Now in this operation, if I simply apply the mass balance, then let us consider this is my control volume. What is happening in this control volume? M dot A is entering and M dot A is leaving. So at inlet and outlet, this is actually same. Okay. On the other hand, in between this I only have a heating coil. I do not have any additional entry of water, and there is nothing from where water can go out. Okay. So if I write the moisture balance, then mass of vapor at the inlet will be m dot A into W1, that will be the mass of vapor content, and mass of vapor content at outlet will be m dot A into W2. Now m dot A is same, it means in this process W1 will also be equal to W2. Is this one clear? Now let's talk about energy balance. In terms of energy balance, m dot A is coming at some thermodynamic state 1. It may have dry bulb temperature of T1. So M1, M dot A is coming with enthalpy H1. And what I am doing in between? Some Q amount of heat is added over here to the air from this heater surface. So Q amount of heat is added, and then what is leaving? Again M dot A is leaving, but now it is leaving with enthalpy H2. Okay. So from here I will be simply getting that Q equal to M dot A into H2 minus H1. Is this one clear? Now, usually for air, I have also specified this point in one of the earlier lectures, that usually whenever we deal with the air, what we try to do? We try to specify its volumetric flow rate. Okay, because typically whatever the blowers, compressors, fans, etc., you will be actually seeing in the market, these are available in terms of the volumetric flow rate of the air. Okay, so whenever we have to define the volumetric flow rate, we follow the STP conditions. Of course, I may need, or the instrument may have to be operated at a temperature of 90 degrees Celsius. Okay, but at 90 degrees Celsius, the density of air will be different than the density of air at 25 degrees Celsius. So ultimately what will be happening? Accordingly, the volumetric capacity of the device will also change with change in thermodynamic state. Is this one clear? Because the moist air which we are handling, its density is strong function of temperature and pressure and even relative humidity with which we are dealing with. So that's why what will be happening, the density, whenever density will be changing, so same amount of air can occupy more volume if density is low, and it can occupy less volume if density is high. But whenever you will be purchasing a fan or say blower, that blower will be having some particular inlet size, some particular outlet size, so volume is fixed, but the density is different. So that's why capacity may become different at different density conditions. So what typically we do at standard conditions, for example, what are standard conditions? Pressure of 1.01 bar, standard atmospheric pressure, temperature of 25 degrees Celsius, okay, and relative humidity of 50%. We define typically the density of the dry air, and density of dry air at all these conditions is given as 1.2 kg of dry air per meter. Is this point clear? Now, whenever I will be writing m dot A, so I can write this m dot A as 1.2 times volumetric flow rate of the air. So V dot A. Okay, and usually for different devices, their capacity is given in terms of cubic meter per minute. Okay, so if you go to industry standards, then the unit of a volume handled by a fan or blower is given as cmm. What is the meaning of cmm? Cubic meter per minute. So it means meter cube per minute. Okay, so if I assume that my V dot A is capacity of the device in terms of cubic meter per minute, here this m dot A is in kg per second. So this V dot A, if I need to convert from cubic meter per minute to cubic meter per second, then I need to divide by 60. Is this one clear? Into H2 minus H1. All are clear with this point? Now, very simple thing. If I am referring to psychometric chart, what I need to do? I need to simply locate my thermodynamic state 1 and state 2, and I can calculate the value of enthalpy 1, enthalpy 2, and I can determine this. Okay. But for locating the state 1 and 2, what I need? I need 3 thermodynamic properties. One is of course pressure, which is normally ambient, and other could be dry bulb temperature and the wet bulb temperature. But at present, if I assume that, say, I do not have sufficient data for locating it, then I may need to derive it from the thermodynamic relations. Okay. So now let's see from thermodynamic relation how I can write H2 and H1. What will be H2? Enthalpy of the moist air, but which is written in terms of per kg of dry air. So what is enthalpy of moist air? 1.005 into T, which is the component associated with the dry air, plus component which is associated with moist air. What is the component associated with moist air? W2 into 2500 plus 1.88 into T2. Correct? What will be H1? Now T1 and T2, sorry, W1 and W2, these are same. So from here I can write H2 minus H1 is nothing but equal to 1.005 into T2 minus T1 plus W times 1.88 into T2 minus T1. Let me replace this value. If I replace this value in the equation of heat transfer, then 1.2 into VA dot by 60 into, again T2 minus T1 can be taken common, 1.005 plus W into 1.88 into T2 minus T1. Is this one clear? Now what is this term? Specific heat of humid air, okay, moist air or humid specific heat. So its value usually at standard condition is how much? 1.0216 kilojoule per kg of dry air. So that is its value. Again 25%, 25 degrees Celsius, 1 bar and 50 relative humidity. Corresponding to this, if you substitute, you will be getting this value. Okay. So 1.0216. Now multiply this 1.2 into 1.0216 into 60. How much is this? Sorry, divided by 60. How much is this? Point 0.0204 V dot A into T2 minus T1, and this has come in kilowatt. Okay, it has come in kilowatt. So it means that if you supply over here the cubic meter per minute, V dot A is cubic meter per minute, you have to remember this point. This V dot A is in cubic meter per minute. So if you supply that this much air, you need to heat from temperature T1 to T2. And which type of air you are heating now? You are not heating dry air. If you heat dry air, then simply 1.005 will come. Okay. You are heating moist air. So if you heat moist air, then this much amount of heat you have to give. Now in this process, you can see that your humidity W1 and W2 were same. So if W1 and W2 were same, it means if you have to represent this process on psychometric chart, how you will be representing? How you will be representing? Say this is state 1. Now W should remain constant. And what should happen to temperature? We are heating, temperature should increase. So this will be the process on psychometric chart. Okay. So in case you have sufficient number of state points given at state 1 and state 2, then by just using these state points you can represent 1 and 2 points in psychometric chart. You can refer to corresponding enthalpy lines. You can read the value of enthalpy from this inclined scale and directly calculate the value H2 minus H1. Is this point clear or not? Okay. In this process, because your humidity is same, it means whatever the water vapor content is there, that is same. It means neither there is boiling or evaporation, nor there is condensation. So it means this process is purely a temperature change process. So you can call this process as sensible heating. And this Q is nothing but the amount of sensible heat that one need to add in order to increase the temperature. Is this point clear? Anyone is having any doubt about this? Let's go for next process, which will be a bit complicated. Is this point clear? Now next process, let's talk about humidification. Okay, what will happen in humidification? Again I have similar kind of duct, m dot A, then some small fine nozzles are there which are adding moisture. Okay, W1 is humidity here, W2 is humidity here, and here you are adding water. So of course this is nothing but water addition. And let's assume this water addition is being done at the flow rate of m dot W. Okay. So now if you write mass balance, you will be, particularly for dry air it will remain same, but for water vapor if you write mass balance, you will be finding that m dot A into W1 is the vapor content at inlet, then m dot W amount of mass we have added, and mass going out is equal to 0. So from here m dot W will become equal to m dot A into W2 minus W1. Is this one clear? Presently let us consider it water addition. Now we will see the cases that if we add water, then what will happen? If we add water vapor, then what will happen? Okay, that we will see further. Okay, is this one clear? Now let's go to energy balance. In energy balance, what will be happening? M dot A into H1 plus m dot W, but m dot W is with what? With some enthalpy. Let's call it HW. Now if it is coming as a vapor, enthalpy will be different. If it is coming as liquid, enthalpy will be different. So let's simply assume it is some enthalpy HW. Specific cases we will discuss further. Minus of m dot A into H2 equal to 0. From here I will get m dot A into H2 minus H1 equal to, in place of m dot W I can write m dot A into W2 minus W1 into HW. All are clear with this point? Now m dot A is cancelling out, so simply H2 minus H1 is equal to W2 minus W1 into HW. Now let's split this. What I can write? 1.005 into T2 for dry air plus W into 2500, and so let's not split it, simply write Hg at T2. Means W means referring to the content of water, Hg at T2 is referring to enthalpy of water vapor in gaseous phase at state T2. Fine. This is W2 and this will be of course Hg2. Minus of 1.005 into T1 minus W1 Hg1 at temperature T1 equal to W2 minus W1 into HW. Clear? First part is very simple, 1.005 into T2 minus T1. Then second part, let's do one thing. In this previous equation, let me subtract in this side minus W2 into Hg1 T1. What I have done? In the left hand side, I have subtracted minus W2 into Hg T1 in the left hand side. So in right hand side also I need to do the same operation. Minus W2 into Hg1 and T1. I did in both the sides. So if I do this operation, what will happen? W2 will become common and inside I will get Hg2 minus Hg. Clear? Inside I will get Hg2 minus Hg1. In the right hand side, I can also take this W1 to the right hand side. If I take this W1 to right hand side, what it will become? This term. Plus W1 into Hg1. Okay. So again I can take W2 minus W1 common in right hand side, and inside I will be simply getting HW minus Hg. Clear or not? Please tell me. No. Because this is minus, I have taken a minus common and that has gone to Hg1. Have I written it correctly or not? Means that's the only argument to the function. Hg we are calculating at temperature T1, but I have written Hg1, it means I am referring to T1 only. Okay? Is this one clear? Now you see, whatever his question was there, whether water is sprayed or water vapor is sprayed. Okay, so I am discussing it, but he is busy in talks. Okay, so now what will be happening? You tell me. If I add liquid water, what will be the scenario? Now there can be three conditions. HW equal to Hg1. Second situation, HW greater than Hg1. Third situation, HW less than Hg. But before that, you simply understand. If I simply add water, what will be enthalpy of water? HW. If water is added in the liquid form, 4.187 into T, that is enthalpy of water. And what is Hg? Hg1 is typically 2500 plus 1.88 into T1. Now, whatever be the water temperature, of course, means in the range of 0 to 50 degrees Celsius. Whatever be the water temperature, 4.187 T will always be less than Hg1. Okay. So if I simply add water, then I will be having the scenario HW is less than Hg. If this is the condition, what will happen to this equation? You tell me. T2 minus T1, and in the right hand side, see, W2 will always be greater than W1 because we are adding moisture content, so it means humidity will be high. So this value will always be positive. Is this one clear? So it means that if I have this situation, then T2 can be lesser than T2. Okay. And if I have this situation, HW is equal to Hg, then this whole will be equal to 0. Right hand side will be 0, and simply I will be getting that this enthalpy content is, because this amount will be negligible in comparison to Hg2 and Hg1. So Hg1 will be, sorry, yeah, so this T2 and T1 will be almost equal to same. So I am getting from here 3 possibilities on psychometric chart. This is my state 1. I have added water. If I am able to add water in such a way HW is equal to Hg1. What it means? I am adding water vapor with the enthalpy content of water vapor equal to that of the enthalpy content of the gas. Okay. In this way, the temperature of the medium will not be actually changing. Okay. I will be finding that the process will be something like this, a vertical line, which may become a pure humidification process. On the other hand, when HW is greater than Hg1, when HW is greater than Hg1, what it means? Water temperature is more, water enthalpy, whatever the water vapor we are adding, its enthalpy is more in comparison to enthalpy of the dry air or moist air, whatever inlet air we are having. It means that we are adding steam at superheated condition in the moist air. Okay, we are adding steam. So when we will be adding steam, though we will be able to achieve humidification, but along with the humidification process now, temperature will also increase. So I will be getting process 1 to 2 days. Now humidification is also taking place. However, temperature is also changing from 1 to 2. Is this point clear? Clear or not? On the other hand, if HW is less than Hg1, it means I am adding water droplets. When I will be adding water droplets, what will happen? Of course, water droplets as such cannot be sustained in the moist air. What will happen in this scenario? In this scenario, the enthalpy of dry air will be utilized to convert liquid water droplet into the vapor medium. So this is the process of evaporative cooling. Okay, so in this process what will happen? In this process temperature will decrease because enthalpy of moist air is being utilized to achieve evaporation of liquid droplets which are added into the medium. Is this one clear? So it means that pure humidification can only take place when the enthalpy content of the water vapor which we are adding, that is exactly equal to the enthalpy content of the moist air. Okay. If enthalpy of water vapor is more, then we will be able to achieve some process in which humidification is also taking place and temperature is also increasing. So this is a process of heating and humidification. And the other process in which when liquid water is added to air, its enthalpy is less, so enthalpy of the air is utilized for evaporating the liquid water. That process will be nothing but cooling and humidification. Where this process is observed, any practical example from common life, cooling and humidification? I told you one example of air cooler. Okay, so desert cooler. What typically is done there? Like water is seeded from the top and then in the cross direction air is actually flowing and air temperature in the room felt is less, but you will be finding that when we run this cooler for longer duration, it increases the moisture content. Humidity level in the room increases a lot because the process happening there is cooling and humidification. Is this point clear? So usually you need to on routine basis supply the makeup water in the cooler. Okay, is this point clear? So in order to achieve pure humidification, what you need to do? You need to control the enthalpy of the moist air. Okay, and the process in which you are able to 100% control the enthalpy of moist air, that process will be becoming what? Only the process of increase in humidity. So I can call it as pure humidification, and along with the pure humidification I can also call it as latent heating process, because sensible temperature change is not observed, only heat is done in terms of increasing the moisture content. Okay. But is it practically possible to supply some water to the air whose enthalpy content is exactly equal to that of enthalpy content of? So it's not practically possible. This type of latent heating majorly happens because of infiltration. Okay, infiltration means this is the room, say you are in some sea region. So close to the sea, you will be finding in that region, you will be having very high humidity. Okay, and you are operating one air conditioning unit inside the room. So that air conditioner has decreased your humidity content. Now across the window gaps, door gaps, some amount of outside air is entering. So whenever that outside air is entering, of course its temperature is slightly greater, but almost you can assume that along with that outside air, whatever moisture is coming, its enthalpy is almost equal to that of enthalpy of the room. Okay, so that process is basically only there it is possible. Other thing is through our respiration. Okay, so whenever we are breathing out, some moisture content is actually added into the room, and whatever the air which we are breathing out, its temperature is almost identical to that of the temperature of the ambient air. Okay, so it means that whatever water vapor we are adding into the room, that water vapor is actually coming at enthalpy equal to that of the enthalpy of moisture present in the room. So it means that process is nothing but a pure latent heating process. Is this one clear? So now let's understand this point again through mathematical perspective. For pure humidification, one necessary condition is there. For pure humidification process, we found that one equation we have H2 minus H1 equal to W2 minus W1 into HW. Okay. Now, condition I gave you that for pure humidification process, HW has to be equal to HG T1. Is this one clear? HW has to be equal to Hg into T1. Is this one clear? Now what will happen in this scenario? Right, let us write H2 and H1. What is H2? This is H2. What is H1? Equal to W2 minus W1 into HW. Now, in pure humidification process, T1 will be equal to T2. Okay. So from here, what I will get? 1.005 T1 and T2 will be cancelling out. I will be simply getting W2 minus W1 into 2500 plus 1 point fine. From here W2 and this will be cancelling out. What I will be getting, that enthalpy of water which we are adding, that must be equal to this value. Okay. Now in this value, here what we have? Yeah, sorry. This part also I can completely, no, I am not able to remove this. I have written it wrongly. Let me write. W2 minus W1 into 2500 plus I will be having some other part also. 1.88 W2 into T2 minus 1.88 W1 into T1. Is this one clear? But what I can do, one assumption I can make over here is that, one assumption of which I can make over here is, what is the assumption? That 2500 latent heat is significantly large in comparison to, yes, difference of the smaller sensible values. Okay, so that's why I can come to this conclusion. Other than this, let me write it in terms of the pure latent load. If I have to write latent load from here, you simply write, what is your latent load? M dot A is the mass handled. Okay, and what happened to that mass? Its humidity changes from W2 to W1. So mass of water vapor at outlet is this. Mass of water vapor at inlet is M dot A into W1 into enthalpy. Is this point clear? And enthalpy I will be simply writing 2500 because that is what I have obtained from here. Is this one clear? After neglecting the small gaseous phase effect in comparison to latent heat. Yes, so that we can achieve pure humidification. If it is different, then this will happen. Okay, but why we are studying this pure humidification process, that let me explain to you. Because whenever we are designing air conditioning system, typically we design air conditioning system for, say, an auditorium. Okay, so in an auditorium what happens? 1,000 people are sitting. So when 1,000 people are sitting for 3-4 hours, then what will happen? Through respiration, whatever the amount of moisture they are adding, that is contributing significantly to the latent heat load on the room. Whenever through infiltration some amount of air is entering from atmosphere, through infiltration that is contributing significantly. So later on, whenever we will be doing the heating or cooling load calculation, there typically the load is calculated in two scenarios. One is pure heating or cooling load, which is a sensible load, and other is latent load. So there this equation will become important. Okay, so again let us convert this equation again in terms of density. So 1.2 density into V dot A by 60 into 2500 into W2 minus W1. Please tell me what is this number? What is this number? 1.2 by 60 into 2500? 50. So 50 into V dot A, W2 minus W1. This much kilowatt is my actually latent heat load. Okay? All are clear with this point or not? What is the meaning of latent heat load? It means that either through respiration or infiltration, if this much load is there on the room, then if on this room I have to control humidity, then I should have equivalent amount of cooling load in the device, which should be able to remove moisture content at this rate. Otherwise my humidity will not be in the controlled condition inside the room. Is this point clear? Point is clear or not? But you have to remember, here we have made one approximation that whatever the sensible component of the vapor was there, 1.88 into T, that we consider negligible in comparison to 2500. But usually whenever we are designing the system for large capacity buildings, for example auditorium, so there this type of engineering approximations works well. Is this point clear? Now from previous equation we can also get one more interesting fact. The general equation is H2 minus H1 is W2 minus W1 into HW. If you recall, I told you when we were discussing about the wet bulb chamber, adiabatic saturation chamber, what I told you? In the adiabatic saturation chamber we were supplying some makeup water. Okay. And I told you that makeup water we typically supplies at which temperature? At wet bulb temperature only. Is this point clear? So in adiabatic saturation temperature, for determining the wet bulb temperature, whatever cooling water, makeup water we were supplying to the chamber, that water was being supplied at enthalpy HF star, and this was nothing but the enthalpy of liquid water corresponding to temperature T star, which was my wet bulb temperature. So on a psychometric chart, if this is my state 1, then if makeup water is supplied at T star, then it will be simply following a line, and that line will be nothing but a constant wet bulb temperature line. So this 1 to 2 process will be along constant WBT line. This is when water is supplied at the wet bulb temperature. If water is supplied at temperature greater than wet bulb temperature, then what will happen? it should have slightly higher slope. If water is supplied at temperature less than wet bulb temperature, then it will be having some less slope. Okay. So it means that the water which we are adding, its temperature significantly controls the process which is happening during the addition of the moisture content. Is this one clear? All are clear with this idea? Okay. Now let me give you one task. You have to do combined heating and humidification process. What will happen in combined heating and humidification? You have heating coil also, you have nozzles also. If I represent this process on psychometric chart, how it will be appearing? This is state point 1. Temperature should also increase, humidity should also increase. So it means it will be something like this. Okay. Now this process I can divide into two portions. The intersection of this horizontal and vertical line will be giving me point 3. 1 to 2 is nothing but combined heating and humidification process. What is process 1 to 3? Only heating. And what is process 2 to 3? Pure humidification. Okay. So I can say that whatever is the load from 1 to 2, that can be given as sum of load from 1 to 3 plus 3 to 2. It means sensible load. So what is this? This is total load. 1 to 3 is sensible load and 3 to 2 is latent load. Is this point clear? Just now I calculated that what is sensible load? 0.0204 V dot A into T2 minus T1. In this case, which process is representing sensible? T2 is not representing sensible, T2 is combined. Sensible is represented by only 1 to 3. So, T3 minus T. Okay. And what is latent? 50 V dot A into W2 minus W3. Okay. The other way of calculating this load is also very simple. From here you can read enthalpy H1, constant enthalpy line, then another constant enthalpy line passing through 2, another constant enthalpy line passing through 3. Likewise on this scale you will get H3, H2 and H1. So total load will be m dot A into H2 minus H1. Sensible load will be m dot A into H3 minus H1 and latent load will be m dot A into H2 minus H3. Clear? Here we define one important parameter which is called as sensible heat factor. What is sensible heat factor? Amount of sensible heat divided by total load, sensible plus latent. So in simple terms it will be becoming m dot A will be cancelling everywhere, H3 minus H1 divided by H2 minus total load. Correct? And in terms of the flow rate of air, it can be written in terms of this 0.0 204 V dot A into T3 minus T1 divided by plus 50 V dot A into W2 minus W3. Now do little bit algebraic manipulations. If you do algebraic manipulations, ultimately you will be finding it will become in the ratio of delta W by delta T. What is delta W by delta T ratio? Slope tan theta. So it means sensible heat factor is a function of slope of humidity by temperature line on psychometric chart. Is this point clear? What it means then? SHF is a function of theta. So how we can do this? On psychometric chart, I told you that we have a scale. Do you have class? You can go, those who have class. Just 1 minute I will be taking. This side we have sensible heat factor scale, and here we have one circle which is called as alignment circle. If for any process I know what is the value of sensible heat factor, this value is given, what I can do? What I can do? Say for a process sensible heat factor is already given to me. Okay, I will be referring to sensible heat factor scale. From that scale, from the given point to alignment circle, I will be drawing a constant, I will be drawing a straight line. Is this one clear? And now, if my state 1 is given, that this is my state 1 and this is the value of sensible heat factor of the process. From state 1, I will draw a line parallel to this line. I will be drawing a line parallel to this line, correct? Now this parallel line now, when I will be taking a horizontal line, correct? And final temperature which is given. Based on that, I can determine the final state. How it is done, we will practice with the help of numerical problems. Okay. So from basic theoretical understanding, we found that sensible heat factor is nothing but a function of the slope. And that important parameter is usually presented in the generalized psychometric chart with the help of a sensible heat factor scale. So behind the specific humidity scale on psychometric chart, you will be finding one more scale where SHF is written. It means it's a sensible heat factor scale. So if for a process the value of sensible heat factor is given, then from that value and alignment circle. What is alignment circle? I have already specified to you. What are the values? 50% relative humidity and 1 bar pressure and 25 degrees Celsius. In some psychometric charts, instead of 25, it is 26.7 degree Celsius. Then, by just using the lines parallel to this line on any other states, I can represent the equivalent process having the same sensible heat factor. Basically, that will be defining what should be the slope of this line for 1 to 2. Is this one clear? So, in many cases, you will be finding that instead of giving the exact thermodynamic states, it will be given that the process have this much value of sensible heat factor. So, that part also you should be able to do. Okay, so maybe 1 or 2 basic processes are left that I will cover in the next class, and after that we will practice some numerical problems.